Hi everyone, welcome to class 3 for PH 125. Today we'll be talking about order of magnitude calculations, scalars and vectors, and one-dimensional kinematics. So let's start with a review of significant figures, picking up where we left off at the end of last video. So remember, when you're working with numbers and you multiply or divide, then your final result should be rounded so that it has the same number of significant figures as the element in your multiplication or division that has the lowest number of sig figs. So, quick example, here I have x, it's the product of two numbers, and I want to determine x with the appropriate number of significant figures. So first thing I'm going to do is to determine how many sig figs each of the numbers in the product have. So looking at 1.263, this one's pretty straightforward. It has no zeros, so it just has 4 sig figs. Next, looking at 0.043, well, my two zeros are both before my significant figures, which means that they are insignificant. So this guy only has 2 sig figs. So what I should do to calculate x is go ahead and multiply those two numbers together, and then I should round it to 2 sig figs, since that's the same number of sig figs as my least accurately known quantity. Okay, so when I do this, I get x equals 0.054309, and I round it to x equals 0.054, so that it has 2 sig figs. Next, let's look at addition and subtraction. So remember, this rule is a little bit different. Instead of looking at sig figs, you look at decimal places, and then you round your final answer so that it has the same number of decimal places as the number in your sum that has the lowest number of decimal places. So, second example here, we have x, it's the sum of two numbers. And so to determine the appropriate number of decimal places in my answer, I'm going to look at the number of decimal places in my two terms in my sum. So looking at the term on the right-hand side, I have all non-zero numbers after my decimal place, so they're all significant, they all count, and so I would say I have 5 decimal places. Here I have a 0 at the end, but we know that a 0 after a significant digit in the decimal place, it counts as a significant figure. And so that last 0 is significant, and we should count it in the number of decimal places that we have. And so I would say that this number has 4 decimal places. Okay, and so now what that means is I should add my two numbers together and round the answer so that it also has 4 decimal places. So when I do that, I get x equals 2.2164. Okay, now it's your turn. So which of these answers represent the product of these two given numbers with the correct number of significant figures? All right, let's see how I did it. So first of all, I just multiplied my two numbers together. And then I thought about the number of sig figs in each of my two numbers since I'm multiplying. So when I look at my first number, I know that the first 3 zeros I have written out here, they don't count as significant figures, but the last one that's wedged between the 4 and the 6, that does count. And so here I would say that I have 5 sig figs. It's these guys right here. Okay, my second number, all of the zeros are significant since they're either wedged between sig figs or after them, and so I would say that I have 6 sig figs. Everything counts in this number. So, number with the lowest sig figs has 5. That means I need to round my final answer to 5 sig figs as well. And so that gives me the answer C. Okay, one last thing about significant figures before we move on, and this is round-off error. So it turns out that when you round to your appropriate number of significant figures at intermediate steps in a calculation, when you get to the final answer, you can have this thing which is called round-off error. And so the best way to explain it is really to look at an example. Here we're going to look at a sample physics problem. Don't worry, this is an example of kinematics, which we're going to get to a little bit later on. And so don't worry too much about this calculation for right now. I know I'm going through it really fast, but that's not the point of this. The point of this is just really talking about round-off error. So when we actually are talking about speed, distance, and time, I will go through this much more slowly, I promise. Okay, so for now, here's our problem statement. We travel at speed 35 miles per hour, which we're going to say is v. That's our symbol for speed. And we're traveling in a car for 0.225 hours, and then we travel at the same speed in a bus for 0.330 hours. Okay, and we want to know what's the total distance that we travel using the equation v equals x divided by t. So I'm actually going to do this problem with two approaches, but before I get there, I need to list out my knowns and unknowns. So this is how I solve every physics problem. Truly, to this day, I was taught to do this in high school. I never stopped. It really helps me, so I highly recommend trying it. Even though sometimes you might think it's a waste of time, I promise you it actually saves you time at the end because you have a nice list of everything you need to know when you're solving the problem, and you don't have to go back and reread the problem statements, which can be like long and kind of confusing. So I highly recommend it. So I write out my known quantities here. I have v, my speed is 35 miles per hour, t car, and t bus. And then next, I also write out my unknowns. So this is how I help myself remember what am I actually solving for. Because sometimes when you're in a really long problem, you can forget. It happens, I promise. It happens to me too, so don't worry. So what is my unknown in this case? It's distance. And so here I'm going to write down my equation that I'm given is v equals x divided by t. And so I can actually rearrange that and get an equation for x, my unknown, in terms of v and t, which you'll see I have both of those things in my known category. So that's going to help me solve this problem. Okay, so now on to my two different approaches for solving this problem. Approach number one, I'm just going to calculate the distance traveled in my car using v times the times the time that I spent in the car. Here that gives me 7.875 miles. And when I do this, I take note of the fact that my speed has 2 sig figs, my time has 3 sig figs, and so I need to round this answer to 2 sig figs, so that's how I get that 7.9 miles here. Then I calculate the distance traveled in the bus by multiplying the speed of the bus, 35 miles per hour, times the time I spent in the bus, 0.33 hours. Here again, I have 2 sig figs for my speed, 3 for my time, and so I need to round to 2 sig figs. That gives me 12 miles. Okay, now I get my total distance traveled by just adding together the distance traveled in the car and the distance traveled in the bus. That gives me 19.9 miles, but now I need to remember my rules for sig figs when I add things, and I need to use the lowest number of decimal places. So here my 12 miles, that has 0 decimal places, so really I should round this answer to 0 decimal places. That gives me 20 miles. Okay, so that's my final answer for approach 1. Approach 2 is really the same, it's just I'm going to go ahead and manipulate my equations before I plug in any numbers. And so this is really my preferred approach. I don't like plugging a lot of things into my calculator. I tend to get a little bit lost. And so I like to really manipulate my equations and get it down so that I have to type in as few things as possible. It's totally up to you. Both approaches are completely good and valid. So I'm just letting you know that approach 2 would be my preferred approach. Okay, so what is approach 2? It starts at the same place. So my total distance traveled is just the distance traveled in the car plus the distance traveled in the bus. But now, instead of calculating those two things out separately, I'm just going to plug them both into this initial equation. So I have v times t car plus v times t bus. And now what I'm going to do is see this v is the same in both of these guys. And so I can factor it out, and I get v times t car plus t bus, where you're adding those two times together before you multiply by the v. And so what that tells me is the total time of travel, right? The time in the car plus the time in the bus. Logically, that's the total amount of time. So this gives me a way to do fewer calculations. So all I have to do is calculate the total time I spent traveling. So I add those two times together. They both have 3 decimal places. And so my final answer should also have 3 decimal places. So I would have 0.555 hours for my total time. Then I multiply that total time by the speed, which is 35 miles per hour, to get the total distance traveled. That multiplication gives me 19.425 in my calculator. And then I need to remember that I need to round to the smallest number of sig figs. Here that's 2 for the 35 mile per hour guy. And so I would round to 2 sig figs and I get 19 miles. Okay, so approach 1 and approach 2, they give an answer that looks really similar, but it's not exactly the same. And so why did that happen? I said they're both good approaches, right? They both are completely valid. But this happened because we rounded at intermediate steps in approach 1, whereas in approach 2, we didn't do any rounding before we got to our final answer. And so that's why we call this a round-off error. So you get a little difference in the two approaches due to round-off error. Okay, round-off error, it's not a big deal. It doesn't mean that you didn't understand the problem. You did understand the problem. So it's really not a big deal. You won't get counted off for it on exams, and Mastering Physics has a tolerance built in for it as well. So you shouldn't get counted off for it on Mastering Physics either. And the way to avoid it, though, is to just keep some extra significant figures in your intermediate calculations. So on that last slide, I was really careful about, calculating out each step, making sure I did the appropriate number of sig figs at each step. But what I could have done to prevent round-off error is really waited until the end to do my final rounding to the appropriate number of sig figs. So you keep track of how many you should have, but then really only do the rounding at the end. And just keeping a few extra is plenty. You don't have to write down every single digit in your calculator. That's way too hard. We don't need to do all of that. Okay, so another topic in this Introduction to Physics chapter is order of magnitude calculations. So sometimes it's really nice to just get a quick estimate when you're trying to solve a problem. So I can think of two cases where it's really nice to do this. The first is when the problem that you're trying to solve is like way too difficult to actually get a real hard, accurate number. So this is an example we're going to look at a little bit later. So these are like big picture questions that it's too overwhelming to try to think about all the variables that you would need to get a really hard and fast accurate number, accurate and precise. And so instead what we want to do is just use a order of magnitude. So base your calculation on orders of 10 basically. All right, another example when we want to do order of magnitude problems is when you just want to do a quick calculation to get an idea for what your answer to a more detailed calculation should be. So say you're going to spend a lot of time thinking about a certain problem, but you want to have an idea in your head for what the answer should be when you get there. And so order of magnitude problems can be really useful for that as well. Okay, and so these order of magnitude calculations, like I said, you really just want to keep data or estimate data in your problem to the nearest order of 10, hence the term order of magnitude problems. You might also hear them referred to as back of the envelope calculations, referring to the fact that you just kind of scratched them out. They're not super precise. Or you might also hear them referred to as Fermi problems, and that's because they were made really famous by this gentleman, Enrico Fermi, who is famous for saying that it's better to be approximately right than precisely wrong. And so he was really fond of these problems, and he did lots of classic examples of Fermi problems, including how many piano tuners there are in a particular city. So we're going to do this quickly for Cleveland. This is a more complicated version. This would definitely be the problem of the first category, that it's too overwhelming to think about an actual precise answer to this question, but we can estimate it fairly well. Okay, so how am I going to do this? And don't worry, this one it's fairly complicated, and so any Fermi problem that we'll be working on in class will be less complicated than this, so don't worry. Okay. So we'll need to do a few approximations, and I'm going to list them out now, and then I'll kind of explain why we need them as we go. So here are my assumptions that I made in solving this problem. All right, next let's get to the problem solution over here. So first thing I want to do in solving this problem is estimate how many homes there are in Cleveland. And so that's where these first two estimates on my left-hand side of the screen come into play. So I'm using the fact that there are about 2 million people in Cleveland. So you'll notice each of these numbers over here on the left-hand side, they have a single digit and then an order of magnitude, right? So it's a single digit times 10 to the something. And I'm actually going to write them out here in the notation like you would see in your calculator. I'm just going to use like 2e6. So e means 10 to the and then sixth. Okay, so that's an extra little shorthand here. So population of Greater Cleveland, 2 million people, or 2e6 people. And I also made the approximation that the average number of people in a home in Cleveland is about 2. So I'm going to use those two things to calculate the number of homes in Cleveland. And so here I would say I have 2e6 people. And then to get the number of homes, I'm just going to divide by the number of people per home. And this is a good dimensional analysis check as well. Okay, so then my people should cancel, and my home is in the denominator of the denominator, which means it moves up to the numerator. So what I'm left with is approximately 1e6 homes. And that's in Cleveland. Okay, next I want to estimate the number of homes with pianos. So how do I do this? Well, I made the guess that approximately 5% of the homes in Cleveland have pianos. I feel like this is probably too high, but there are schools and there are also churches, so I thought maybe it was an okay approximation for the purposes of this problem. So all I would do is take the total number of homes, that's 1e6 from above, and I just multiply by 5%, which is 0.05. Okay, and so when I do that, I get 5e4. And that's homes, oh goodness, with pianos. Sorry, I ran out of space. Okay, so 5e4 homes with pianos. I'm assuming that each of these homes only has one piano. And so that tells me that I also just have 5e4 pianos in Cleveland. All right, so that's my approximation. So you were probably wondering where I was going with this, but that was my approach to approximating the number of pianos in Cleveland. Now I need to figure out how many hours it would take to tune all of those pianos, and I'm going to do this per year. So let's say how many hours per year do we need to tune all of these 5e4 pianos? Okay, so how would I calculate that out? Well, that's where this second to last approximation comes in. I said that it takes about 2 hours to tune a piano and that each piano needs to be tuned once per year. So I thought that seemed pretty reasonable. And so then if I have 5e4 pianos, then how many hours per year would it take to tune all of them? I just do 5e4 pianos and I multiply by 2 hours. And that's per year and also per piano, right? So that was our 2 hours per piano per year. My pianos will cancel. And I'm left with, when I multiply this out, I get 1e5 hours per year. Okay. So that's a lot of hours. So now we need to figure out, that's the total number of tuning hours that we would need per year. So the next thing we need to solve this problem is how many hours could a piano tuner work per year, right? And so then if I know that, I'll be able to divide to get the total number of piano tuners we would need to tune all of these hours. So that's the approach here. So how many hours does a piano tuner work? That's my last estimate over here on the left-hand side. I guessed 40 hours per week, that's pretty standard. And we'll say they work 50 weeks per year, so they have 2 weeks of vacation. That's pretty limited, but okay. So at 40 hours per week and 50 weeks per year, the total number of hours they work would just be 40 hours per week and then multiplied by 50 weeks per year. Okay, so then my weeks cancel, and I'm left with 40 times 50, so that should just be 2,000, which I'm going to write as 2E3. And that should be, sorry, my weeks cancel, and so I get hours per year. And that's really per piano tuner, right? I should have written that in here. That should have been in the denominator over here, 40 hours per week per tuner over here. Okay. And so then that's great. So now I know how many hours each piano tuner can work in a year. I know how many total number of hours need to be worked, right? That's the number of tuning hours that we calculated. And so all I'm going to do to get the number of tuners is take 1E5, and that's hours per year. And then, oh, I should have, I'm sorry, I'm going to rewrite that a little bit. Okay, hours per year, because I want to have a bigger denominator down here. And then I'm going to divide by 2E3 hours, and that's per year per piano tuner. Okay, great. My hours cancel, my years also cancel. My tuners are in the denominator of the denominator, which means they move up to the numerator. And so I end up with the correct dimensions, which is number of tuners, so that's great. And so then all I'm left with is this pretty easy division, right? 1 times 10 to the 5th divided by 2 times 10 to the 3rd, and that just gives me 50. That's all I'm left with, 50 piano tuners. So that's my approximation. I think we need about 50 piano tuners in Cleveland, and feel free to let me know what you think about that approximation. Okay, so as you can see, we just kept, one single digit with an order of magnitude throughout this calculation. It made the calculation pretty fast. I did all of that in my head without a calculator, which is really nice, and it gave me this rough approximation. So it might be off, but hopefully it's on the correct order of magnitude. Okay, and so then actually this is the last topic in chapter 1, and then we'll be ready to dive into some real physics. So last topic in dealing with quantities in physics is talking about scalars and vectors. So a scalar is a quantity that is just specified by a number, a quantity, it has units, and nothing else. So examples, temperature is a scalar, so 70 degrees Fahrenheit, 70 degrees Celsius, that would be hot, and so it's a scalar. Or we could say the car is traveling at a speed of 55 miles per hour. That's also a scalar. The runner has traveled a distance of 5 kilometers, also a scalar. Okay, so example here, the speed that you read off of your speedometer, 55 miles per hour in this case, that is a scalar. The other type of quantity we talk about a lot in physics are vectors. So vectors are specified by a quantity with a set of units and also a direction. So for example, the train is moving north at a velocity of 80 miles per hour, or the bicyclist has traveled through a displacement of 60 kilometers southwest. So both of those quantities are specified by both a magnitude and a direction, a magnitude with units and a direction. Okay, so here I've drawn my train and I've drawn in this arrow here. So that's telling me the direction that the train is traveling in, which in this case is southwest. And that's pretty common for working with vectors. A lot of the times we draw them as arrows. Vectors are really, drawing vectors as arrows is really nice because it gives us a way to talk about both direction and magnitude. So the direction of the vector is just the same as the direction your arrow has been drawn in, so that's pretty straightforward. The magnitude of the vector is represented by the length of the arrow. So longer arrow, bigger magnitude vector. When we're writing things down, it gets a little trickier to specify between vectors and scalars, but it's really important to keep track of whether what you're talking about has a direction or not. And so what we do when we talk about vectors is we use bold font if it's in a text. You might also see, and I will always use this notation, bold font with an arrow over the top. Or if you're writing it down, it's hard to write in bold, so it's just written down normally, but with a little vector arrow sign over the top, like the vector arrow from the text. Okay, if you're just talking about the magnitude of the vector, or if you're talking about a scalar quantity, then what you want to do is represent it either with just plain text, that would be if you're talking about a scalar, or you can represent a magnitude of a vector using these absolute value signs. So that tells you that you don't want to think about the direction. So only thing you care about then is the magnitude of the quantity. So absolute value signs around a vector, that tells you that you just want to deal with the magnitude, but also sometimes we get a little lazy and we want to just write down the magnitude of the vector as just plain text. And so whenever you have plain text, assume that you don't need to talk about the direction. Okay, and feel free to call me out if I get lazy and I forget a little vector sign on something. It happens. It happens to the best of us, I promise. Okay, all right. So last tips for problem solving in physics, just to wrap up chapter 1. So first thing I want to say is that there are many ways to solve a physics problem. So if I'm giving an example and you thought of solving the problem a different way, as long as you're applying the relationships, your way is perfectly as good as my way, I promise. You will get the right answer, the same answer. And so there are many ways to approach a problem. You will notice if I've already written out some notes and then I rewrite a problem solution, I probably won't solve it the same way twice. It's very hard to solve a problem the same way twice, actually. So don't worry if you see me solving something a different way than you did. You can always ask, but generally speaking, as long as you're applying the relationships correctly, your way is perfectly good. Okay, some helpful suggestions for problem solving. Like I mentioned earlier, writing down your knowns and unknowns is really beneficial. It really helps you think about what you've been given, keep that information organized, and then you don't have to keep digging through the problem statements, which can be really wordy and kind of awful sometimes. So it's really nice to just have it written out in a list. And also writing down the unknowns helps you stay on track with solving the problem that you're being asked to solve. Another thing is putting a box or a circle around your final answer. This is helpful not only to me as the person grading your work, but also to you, because it helps you, like if you skipped a problem and you come back to it, you see the box, then it tells you, oh, I did finish that problem. It also lets you, look at the boxed answer, look at your unknowns, and make sure that the boxed answer is the thing that you were supposed to be solving for. So it has many benefits. I already mentioned this in our first video, but I'm going to say it again. Plug and chug, it really just doesn't work. I know we want it to work, but it does not work. So I would highly recommend trying to understand relationships rather than just plug in numbers to problems that you've seen solved before. It doesn't always work out. Physics is about problem solving, not memorizing. That's why we give you equation sheets. Okay. One more tip, making sketches can be super helpful. So especially when you have a really complicated problem statement, if you make a little sketch, it can really help you out a lot. And a lot of these problems are based on, kind of forced, but real world applications. And so your intuition should usually guide you in the right direction. So if you sketch it out, you might get an idea about, what your answer should be. That will help you at the end when you get your answer. You can think back and be like, oh yeah, that does make sense, right? So that's always a good thing to do. And then finally, check your answer, a few checks. Checking the units is always great. Make sure that the number that you calculated at the end has the units that you expect it to. Does the sign or direction make sense based on the drawing you did, the little sketch? Is the quantity realistic? So, if you're asked for a person's mass and it's just like really tiny or really huge, right? So if it's 400 kilograms, that's pretty big. So you maybe made a calculation error. So these problems are supposed to be somewhat realistic. So I would definitely try to keep a few realistic benchmarks in mind. Okay, and that's really it for chapter 1. We're going to do a quick little bit on one-dimensional kinematics to finish up this slide today. Okay, so chapter 2, one-dimensional kinematics. What are kinematics? That's probably the question you're wondering right now. And so remember in the first video, I talked about how we're going to be studying mechanics this semester, which is the physics of motion. So this physics of motion, it can be broken up into two different categories, kinematics and dynamics. So we're starting with kinematics, which is just the study of motion. So basically, it's just recording things about motion, not talking about how the motion was created. That's reserved for the second or for the later parts of the semester where we'll be studying dynamics. Dynamics is the study of how motion is created, and it turns out it's in response to forces. So we're starting with kinematics, the study of motion, and we're going to start in one dimension. Okay, so one-dimensional kinematics, the starting place are these measures of length, and we have three measures of length that we talk about in physics: position, distance, and displacement. All three of these are, again, they're measuring length, and so they're measured then in SI units of meters. Okay, so the first thing we're going to talk about is position. It's denoted in one dimension with just an X, and here you'll notice that it's a bold X with an arrow over the top, which tells me that it is a vector. Okay, and so the location of the position then is the location of an object relative to a defined coordinate system. So here I have a man drawn in, a stick figure man, and he is on a coordinate system that I have drawn in here. My coordinate system consists of an arrow pointing in the positive x direction. So the arrow always points in plus x. Okay, so in this case, I would say plus x is pointing to the right. And then my coordinate system also needs to have an origin. So here I have a line that's marked as x equals 0. That's my origin. Okay, so then I would draw my little guy wherever he is and mark his location as x initial on this coordinate system. So this is a kind of the shorthand. You'll see this a lot where it's just marked in as xi, even though we know, I already said, it's a vector. And so realistically, it should be represented with an arrow pointing from the origin to the place where our person is. So here, really the position vector in this case would be the arrow pointing from the origin to x sub I, and it would be denoted with x sub I with the arrow over the top. Okay. And in one dimension, vector directions are given by signs. So it will be in the, to the left is the negative direction in this case because I've drawn my positive direction going to the right. Okay. And then the next measurement of length in one-dimensional kinematics is distance. Distance is denoted with a lowercase d, and it is the total length of travel. So first thing I notice here is, unlike position, distance is a scalar, right? There's no vector symbol. And what that tells me is that it should always be positive. So you should never have a negative distance. Since it's a scalar, it doesn't have direction. And the plus and minus, that's really just telling us direction. And so you never want to have a plus or a minus on a scalar quantity. It should just be the plus value. Okay. So distance, it's always positive. So let's look at an example here. I have my guy. He's on his coordinate system. Now I've told you that his initial position is at -3 kilometers. That little I, that's what I meant by that initial, x initial. Okay. And so let's say this little guy, he walks home, which is at a position which I'm calling x intermediate or x int. And this position is -0.5 kilometers. And then he walks to school. And so his final position then is at +0.3 kilometers. What is the total distance this guy travels? Well, I'm going to calculate it out by first calculating the distance he travels to his house. So here that would be 0.2 kilometers, right? Since that's the, that's the difference between his initial and intermediate locations. It is positive even though he was moving to the left because distance is always a scalar. Next, I want to calculate the distance he traveled from his house to school. That's 0.8 kilometers. And so then the total distance he travels is just the sum of those two, which is 1 kilometer. Okay, our final measurement of length that we're going to talk about in here is displacement. In one dimension, we call displacement delta x. And here, this delta is the triangle symbol that you see there. We're going to use it quite a bit. It just represents change in. So anytime you see delta, you can read it as change in. So here I have delta, x was position, so displacement must be change in position. Okay, and mathematically what that means is we're always taking the final position minus the initial position in this case. So anytime you have delta, it's always final minus initial. All right, it's also a vector, and in one dimension then its sign, just like position, will be given by a plus or a minus sign. So let's look at our same example as we looked at for the distance calculation. Here we want to know the displacement of our little guy, and so that would be the final position minus the initial position. In terms of a vector, I would draw the arrow pointing from the initial position to the final position, and that is his displacement. So that's the red arrow I've drawn in here. Okay, to calculate the change in position or the displacement, I literally just plug into the equation that I've written up top here. So delta x equals x final minus x initial. X final is plus 0.3 kilometers, x initial is minus 0.3 kilometers. And so I have 0.3 minus a minus 0.3, so that becomes plus 0.3, and I get plus 0.6 kilometers. So that would be my displacement from my initial position to my final position. It makes sense that it's positive, right? Because this arrow is pointing in the positive x direction. All right, let's wrap up with some quick questions to make sure that we understand the concepts of position, distance, and displacement. So you drive 5 miles from your house to the grocery store and back, and we want to know what is the total distance that you traveled. Okay, when I solved this problem, I thought about what grocery store is about 5 miles from my house, and that would be Heinen's for me, the one on Green Road. So I was thinking I would draw that in here, and I picked a coordinate system. So I wasn't given any coordinate system in this problem, so I just kind of picked it. You can do that. It is allowed. All you have to do is make sure you use the same coordinate system throughout the whole problem, and then you're good to go. So here I've chosen mine so that my initial position is at the origin, or at x equals 0. So I'm at my house. I travel a distance of 5 miles to Heinen's, and then I turn around and travel a distance of 5 miles back. Distances are always positive, so the total distance I traveled would just be 10 miles. That's C. Okay, last one. Now we want to know, what is your displacement? Same problem. Okay, here we go. I drew the same little sketch as last time. This time I want to think about my displacement, which remember is change in position. So I would say my final position in this case is x equals 0. My initial position is also x equals 0. And so my displacement, delta x, is x final minus x initial. 0 minus 0 is 0. So I would get A. All right, I'll see you in class.